Hello and welcome to the COMSOL tutorial on continuation method. So we're going to implement various continuation algorithm and specifically focus on implementation of arc length continuation and limit point calculation in COMSOL. So Dr. Kumar has already covered these algorithm in the class in great detail and also shown MATLAB implementation of these algorithms. So I'll just going to show the COMSOL part in today's demonstration. Just for the sake of completeness, I have just shown the main idea behind different continuation algorithms using these schematics. So the problem statement is we want to solve this system of nonlinear equation for various values of lambda. Lambda is our parameter and u is the vector of unknowns. So the idea is very simple. Say for a given value of parameter lambda naught, we find the solution using Newton method. So the solution is u naught, and then we use this solution as the initial guess for solving for next parameter values. So say our next parameter lambda 1 is at a step of delta lambda from your first solution, which you already know. So we just use the previous solution as initial guess for the next parameter value, and if the above steps doesn't converge, then a smaller step is chosen in the lambda. So we reduce this step size delta lambda and use the same method. So the summary of this method is use the previous solution as initial guess for the next parameter value. And the other algorithm is Euler-Newton continuation. So in this case we construct a tangent from the previous solution. So we use the slope calculated at the previous solution, and using that we find the initial guess for the next parameter value. So in the previous case we just use the same previous solution as the initial guess for the next parameter. In Euler-Newton continuation we construct a tangent using that slope at the previous solution and find the initial guess. And as I have pointed out here, both of these options are available in parametric solver in COMSOL, and we'll look at those. So we have seen this example before, so let us quickly implement this continuation on this single nonlinear equation, van der Waals equation of a state with P as a parameter, pressure as parameter. So let me click on COMSOL, and I will just not going to build this model but quickly open this model which we built in the last demonstration. Okay, and let me just quickly show you. So this is the list of parameters. P is pressure, A, B constant, R is gas constant, T is temperature, and V naught is the specific volume calculated using ideal gas law. And we have entered our van der Waals equation in this form. So now for continuation we just need to click on the stationary, and in the extension we need to check this box which says continuation, and then we need to add the parameter. So P is the parameter, pressure, for which we want to carry out the continuation study. So select OK. Then we need to define a range of this. So you can click this. We want to start from 1 and stop at say 50, and we want to take steps of 1, and we can just add this. So now let's just quickly run this. So I right click, study and compute. So it has solved for this, and you can always click on the state variable V and generate a table for all the parameter values. So it shows the specific volume corresponding to each value of the parameter P, and we can always plot this. Okay, so this is how your solution changes with parameter P, and Now let me quickly show you the parametric solver details. So if you expand this node solver configuration and then solver, go to stationary solver, and then if you click on parametric, then you will see this drop down menu which says predictor, and right now it is on automatic. So if you click this, you will see two choices here. So one is constant predictor and one is linear predictor. So constant predictor is when you use your previous solution as initial guess, and linear predictor is your Euler-Newton continuation where you construct a tangent. And so COMSOL automatically determine which one to use, and you can always select one of these. So but I just wanted to relate those with COMSOL what we have seen in the class. So the arc length is not implemented in COMSOL, is not inbuilt like the Euler-Newton continuation or Newton continuation, but we can implement it in COMSOL, and we're going to see the example in a bit. Okay, so let's go back to the slides here. So we have just implemented the simple continuation on the van der Waals equation of state. Now the problem with this Newtonian continuation is that it cannot track this kind of turning solutions, the solution with these turning points or limit points. Okay, so at these points the Jacobian becomes singular, and the Euler-Newton or the simple Newtonian continuation cannot track this full solution. It might jump from this branch to the other branch, but it cannot track this full completely turning solution. So for this case we need arc length continuation, and again Dr. Kumar has covered this in the class. So the main idea behind this is we reparameterize this problem in terms of arc length. So we treat our original problem parameter, which is lambda in this case, as an unknown, and now the continuation is performed with respect to new parameter, which is the arc length in this case. Okay, so the overall the system of equation has an additional equation which relates arc length to these original parameter and the system of or a vector of unknowns. And so let us see the next slide. So this is our original equation, f of u and lambda is equal to 0. Now to implement arc length continuation, we add another equation which is shown here, n of which is a function of u, lambda and s is equal to 0. Here s is your arc length parameter. So now we have an extended system of equation, and we treat the original parameter lambda as an unknown in addition to our original vector of unknowns u, and s is our arc length parameter for with which we going to going to use this as a new parameter for continuation. So so now this additional equation which is shown by this capital N, it can take any shape, like for example it can take any form, like one I have shown here is based on simple you can write this using Pythagoras theorem, that arc length square is equal to du square and d lambda square, and the same equation can translate to u minus u naught square, lambda minus lambda naught square, where u naught and lambda naught are our known solution on this curve. So for u naught is the solution for the corresponding lambda naught parameter value, and if you differentiate this equation with respect to s, then from this equation you can get this equation, the last equation shown in here. And Dr. Kumar has used this equation for arc length implementation in MATLAB, and we're going to use the this equation, the number 3 equation. So the main idea is, again, we add additional equation, and we have an extended system of equations now, and our original problem parameter lambda is now treated as an unknown, and we have reparameterized this whole system equation with respect to a new parameter arc length, and this additional equation relates arc length to our original parameter lambda and u, which is our unknowns. Okay, so with this, let's try arc length continuation for this very simple nonlinear single equation. So the function I have shown here, and the bifurcation diagram for this is shown here, how the state variable x changes with the parameter a. Okay, so let's implement this problem and see how we can do it. So let me open a new, so I don't want to save this. I again open a 0D and go to next, and I'll select global ODE and DAE, then click next, and I choose stationary study type and click finish. Okay, and in the global definition, I'll right click, add parameter, and add a parameter a is equal to 0.1. okay, a is our parameter, and in the global equations table, I will in the first column I will write x, which is my state variable, and my equation is a times exponential of x minus x. So let me just check if my equation is right. So ax minus x. Okay, so we have entered the equation, and we need to give initial guess. So let me just give, say, 0.1, and let us just solve for only this parameter value of a is equal to 1, which we have specified in the parameters. So if I say compute, it has solved this, and let me just clear this log for the next calculations. And we can always look at the value when you see the state variable here. You can generate a new table, and your variable for the parameter value a is equal to 0.1 is 0.1118. okay, now let's just do the Newton continuation. So I'll click on the stationary, go to extension, and I do continuation with respect to parameter a, and I give a range of values starting from 0.1. let us go till 0.8 in the steps of 0.01. okay, so I add this, and then I say right click study and say compute. Okay, now the error is failed to find a solution for all parameters. So I say okay, let's see, and so you can go to this parameter selection, and from, if you select this from list, it will show you that it has calculated from 0.1 till 0.37, but you cannot trust this last value. You have to go back to the log and see if the solution has converged for 0.37 parameter value. So if I go to the log, I can see it has converged, and then you can see how quickly it is just taking one iteration for getting solution for these next set of parameter values, and it keeps going till 0.36. solution is converged for 0.36, but for 0.37 it doesn't converge, and damping factor reduces from 1 to 0.3, and because it is not converged for 0.37, it reduces its step size, the solver, and then it tries to solve for a parameter value of 0.3625, and it converges for that parameter value. Then it tries for the increases the step size, and then it tries 0.3675. It converges for that value as well, but for 0.37 it doesn't converge. So and we know that this is where roughly the limit point is, so we expected that Newtonian continuation will not work. But let us just run one more time the Newton continuation with a different gas. Okay, and so if I give the gas instead of 0.1 to say 2, and let's see, and let me also change this, because of 0.28 instead of 0.28, let me just make it 0.36, because we know 0.36 it should calculate the solution. So let's say compute. Okay, so it has finished. And we can again plot this. Okay, so let's just generate a new table. So this is the solution, and if I change my gas to 5 and then click compute, I'm just changing initial guesses just to see if it goes to the other branch. So let's again see and generate a new table for solution. Yes, so now the solution is different from the previous one. So as we have changed this initial guess for x, now the solver has converged to a different solution, and we can plot these solutions. So I'll just plot this part, and in the same plot, if I right click and add the table plot, and in this one let's use table 1, and if I plot, so, and sorry, we need to choose table 2, I guess. So this will show you the two branches of the solution which we have obtained using Newton continuation, the continuation method which is inbuilt in COMSOL, but still it doesn't track the complete solution and it fails near the limit point. Okay, so we can implement arc length continuation and it should be able to give us the full solution. So if we want to now implement arc length continuation, we need to add an additional equation, and we will need to treat our original parameter a as unknown. So let me write this additional equation, and so we're going to use the additional equation of this form which I have shown here. Okay, and this lambda naught is u naught is a solution which we have obtained using Newton or any known solution on the curve. Okay, so let me just write this equation. So a, which is the original parameter, is now unknown, and I will write my additional equation as w1 is the weighting function, and x minus x naught square, I missed this, plus w2 times a minus a naught square, and we need to take s to the left hand side, so minus s square is equal to 0. So this is our additional equation. Now remember, x naught and a naught, we need to give these values from this. So let us just say for a value of 0.23, our state variable is 2.3046. So I'll just replace these values here. For a value of 0.23, so I'm giving a reference point here, value of 0.23, my solution is 2.3046. okay, Now I need to choose my weighting functions or weights for these two terms. Okay, so there could be many choices, but the general idea is to make these all the terms of same magnitude. So because x is greater than this a values, we are going to choose w1 as 0.1 and we will keep w2 as 1. So let me just declare these. So w1 is 0.1 and w2 is 1, and also we need to declare s, because now we're going to carry out continuation with respect to s, which is our arc length parameter. Okay, so we have defined our additional equation, and also now look at, if I'm going to say carry out continuation for s, so let me remove a from this and add s values and say okay, and let me give this range starting from 0 and stop at say 1, and in the steps of 0.01. okay, and I add this. Now I just want you to see what will happen for s is equal to 0 value. So if I just go back, for s is equal to 0, since this complete equation is equal to 0, the solution should go to a parameter value of 0.23 and a state variable equal to 2.3046. So for s is equal to 0, we should return solution same as of your reference point, and then as we increase our arc length parameter, it should track the full solution which we have seen earlier. So let us try this and see. And also we need to give now initial value for a and because our initial point is this, so let us just give initial value close to the initial reference point. Okay, and now let me just say compute. So it has computed the solution for parameter s is from 0 to 1 in the steps of 0.01, and let me just go back here and let us get this solution vector in a new table, and also let us see the value of the original parameter a in the same table. Okay, and let me just plot this solution maybe in the new plot first, and then we will keep it in the okay. Now this funny diagram, if you see, it is just because we have not plotted the state variable with the x with the parameter, original parameter. So you can just go to this table plot 2, and then you can select x-axis as your state variable a, which is our original parameter, and then plot columns. In the manual you can select a state variable x and then click. Okay, so this is the how the solution looks like, and we can just now plot it in the same plot as our previous Newton solutions. So I'll add another table plot in this one, and let me select the table 4. In the x-axis I'll select state variable a, plot columns I'll select state variable x, and let me change the color to black, and let me put a marker with diamond sign. Okay, so we can see that it matches these two branches, and also it tracks the limit point, and it continuously we can use to track the full solution using arc length continuation, right? And like the key here is to map your arc length parameter with your original parameter A. Like in this case, this range h is equal to 0 to 1, it starts from a parameter value of 0.23 and then it goes back beyond 0 to a point of 0.3 or more. So we can always tune this for how many for how much parameter value you want to run this continuation, and appropriately it will give you a range of solution corresponding to the original parameter. Okay, so we have implemented this continuation, arc length continuation for this simple problem, single nonlinear equation. Okay, and now let us move on to the next example. So this is the example Dr. Kumar has implemented in MATLAB. It's the reactor stability problem. Just neglect this transient term here, and if we equate it to 0, then we have two nonlinear coupled equations, and the parameters are given here, and these are the three steady states possible for a given parameter value. Here Q, the flow rate, inflow rate, is the parameter. So let me just quickly, maybe I'll just, in the interest of time, I will open the solved model and I will walk you through the model, and we will spend more time on the limit point calculation. So let me go to this CSTR stability combined arc length model and open this for you. Okay, so first step is we have to declare all the parameters. So this is taken from the slide which I have shown you. Okay, and I'm going to upload all these files, COMSOL files and the PDF files on Moodle. So first step is to declare all the parameters, and then we need to write these equations. So the first two equations are the original equations for state variable A and T. A is concentration and T is temperature. Okay, and okay, now if you just solve, for example, say just these two equations, and you do the continuation, then you're going to see these two these plots, like just the blue and the red curves. So let me just disable the arc length plot by right clicking and disable. Okay, so now what I have shown you here is simple continuation plots for the state variable T for the range of parameter Q from 1 to 30. Okay, and now we have here two curves. So the first curve is the okay, let me also show you this. The first curve is coming from table 3, and so if you click on table 3, you can see table 3 shows the forward path. So it starts from 1, and then we are incrementing in the steps of 1 to a value of 30. Okay, so this plot, the first part is this, how, and then it jumps to the next branch. It cannot track the full turning point solution, but it jumps to the next branch. Okay, and so this, the blue line, blue curve corresponds to the forward path. So maybe just let me rename this as forward. Okay, and then this other plot is when you start from Q is equal to 30 and then track back for parameter value of 1, then it takes a different path and then jumps back to this branch. And so let me rename this as reverse. So these are the two simple Newtonian, Euler-Newtonian continuation applied to this CSTR problem. and we can see that solution jumps from one branch to the other branch, but it doesn't track the full solution, because we know at limit points the Jacobian of the original system of equation is singular, and therefore there is a need for arc length continuation to track the full solution. And as we did in the last example, we need to add an additional equation, and it is of the similar form which we have used in the previous example. So again, it is now the a minus a naught square, t minus t naught square, and lambda minus lambda naught square. So here our lambda parameter is q, and so this a naught, t naught, and q naught is the reference point, and you can look at this continuation solution from where I have. So this is the reference solution I have chosen. For q is equal to 15, my a is 0.0047 and state variable is 303.1134, so which is I have given here. And then s values, again I have started from s is equal to 0.5 to I have done the continuation from 0.5 to 34, and this range of values you have to choose from trial and error, and you need to see how this arc length parameter maps with your original parameter of the problem. For example, in this case it is q. Okay, so when you run this problem extended set of equations, you're going to see the full solution. And I'll just enable this by right clicking this table plot, and this table corresponds to 11. So let me show you the 11 table, where I have the data for all this continuation data with respect to s, and I have listed here the state variable a, state variable t, and our q, which is the parameter of the problem, but now is a state variable in the extended system of equations. Okay, so when you plot this, you'll see that this arc length continuation captures the complete solution, and it tracks the even it goes through the turning points. Okay, so I hope with these two example arc length implementation in COMSOL is clear. But let me also point this out, that it is not done in the exactly same way as shown in the class by Dr. Kumar using MATLAB. So I'll leave you to figure out what is the difference between this COMSOL implementation and the MATLAB implementation which Dr. Kumar has shown in the class. Okay, now we'll move on to another very interesting problem: how we can exactly calculate the limit point. So we know approximately using this figure where are the limit points, but we can exactly calculate using this formulation shown here. Okay, and Dr. Kumar has already talked about this part also. So the idea is to find the point where the eigenvalue, exactly one eigenvalue, goes to 0, and so you equate that eigenvalue problem to 0, so your Jacobian is singular, and just to make sure that the corresponding eigenvector is not 0, we add an additional equation. So say we have n equations, the original equation, then the second equation, your Jacobian, this also second equation also represent an equation, and then we add one more equation to make sure that this eigenvector is non-zero, and we are really enforcing that Jacobian is singular. So this system of equation is valid for limit points, and if we solve this, we should be able to get our state variables a and t in this case, and also the parameter value, so we can find out the limit point in the bifurcation diagram. Okay, so again, since it is a non-linear system of equations, we can implement it in COMSOL using the same method which we have seen in the previous demonstration. So let us quickly implement this and see if we can estimate the limit point. So let me go back here. So let us just modify the same model. Okay, so now we do not need this additional equation for arc length continuation, so I'm going to remove this equation. Okay, and maybe just delete this part. Now we need Jacobian calculation in this, so I will just copy this and declare it as a variable function. Control C, and in the variables I'll just say f1 and write this expression, copy this expression, and similarly I'll take this second equation, complete equation, copy this and declare it as another variable f2 function. Copy this. So all I've done is I've just copied these two equation functions. Okay, and I have done this to easily calculate my Jacobian equations, the second equation which I have shown you. Okay, so I have these two equations, and then the other equation, let's say for Q. So we have now 5 equations, and now we have 5 state variables. So Q is the third variable, and let me write down the first equation. It will be, say, J11 times P1 plus J12 times P2. Okay, so first term in the Jacobian, the 1 1 entry in the Jacobian multiplied with the P1 vector, and the second entry in the first row multiplied with the P2. So let me write, so first term for the Jacobian will be d of f1. We have declared this first equation as f1 with respect to your state variable A times, say, P1 is the component of eigenvector plus, which is unknown, and d of f1 with respect to P times P2. Okay, so this is our third equation, and I will just copy this and paste this here. And now our unknowns are P1 and P2, so I'll write P1 here, and I need to make it the second equation with Jacobian. So this derivative is now taken for the function f2 with respect to A, and the second term is f2 with respect to t times P2. Okay, and the last equation is some norm of P, just to make sure that P is non-zero and only we are forcing Jacobian to be 0. So it will be P1 square plus P2 square minus 1. Okay, now we need to give initial values for these, and again because these system of equation will utilize Newton method or damped Newton method, we need a good initial guess. So let us just see this plot here. Oh, the plot is in the same. So the plot is, we know the limit point is somewhere close to, say, I would say close to 7 and 310, and we know like where are we? Yeah, so these values are okay. For Q I'll just give a value of 7, and for P1 and P2 I'll just say 0.5 and 0.5. Okay, so if it doesn't converge, then we need to change initial guess. And so let's just, before computing, let me go to stationary and uncheck this continuation, because we are not solving continuation problem, but we are just solving a extended system of nonlinear equation to estimate the limit point. So this is that extended system, and it should give us the A, T and Q value for limit point. So let me just right click and compute this, and looks like it has converged. So let us look at the results. So if I click on A and say show me in the new table, the variable value is 0038, the T value in the same table is 310.69, the Q is in the same table is 7.6351. okay, so if I go back to the plot and see 7.63 with 310.69, so let me just zoom in to see 7.63. So it approximately calculates me the limit points, and similarly I think we can estimate this other limit point, and we just need to give initial guess close to this point. So this is how we carry out the limit point calculation in the in COMSOL. Okay, so let me see what is left. Okay, and so in a similar fashion we have till now we have seen only linear or non-linear algebraic equation, but we can also solve ordinary differential equations or coupled ordinary differential equations. So I'm just going to walk you through this simple examples, which is a boundary value problem. Okay, so let us do this. It is related to your assignment problem, so I'll just show you this boundary value problem implementation in COMSOL. So again, if you click on new, and I'm not going to save this, if you click on new, now you need, because it's an ordinary differential equation with the independent parameter x, we need to choose 1D problem. It's a boundary value problem, and I click next, and I select, I need to choose. So now we need to choose an interface for which the equation structure closely relate to the equation that we want to solve. So our equation has second order term, so we can just go here, and in the mathematics there are either we can use the PD interface, the coefficient form, it's a general form for any PD, or if you go to classical PDEs, there are all of these equations with second order terms, so we can choose anything, and appropriately we need to define coefficients. So we're gonna see this, and since we have two equations, let me call this dependent variable u1, and then I'll add this one more time. Now I will call it u2. So I have two equations with variable u1 and u2. Then I click next, select stationary, and finish. It will generate all these nodes, and two nodes for the physics heat equation, and you can look at this equation form. So if you see, there is a time dependent term, time derivative here, and then this term is the this del is dou over dou x gradient, and so this is similar to our equation. So for time dependent term is 0, and the coefficient for the second order term is 1 over 5. So let us just declare that. So our dA is going to be 0 because this term is 0, and C is 1 over 5, and so we have taken care of the for second order term and the time dependent term. and here is that. Yes, so this remaining term we need to pack in the source term f. Okay, so and we need to declare the parameter lambda as well. So in this case, let me just open this model and walk you through again just to save time. So I have this model here, coupled boundary value problem. If I open this again, I have the same model. So let me quickly walk you through this part. So in the parameter I have declared lambda, which is 1, and in the geometry I have chosen a one-dimensional interval going from 0 to 1. Okay, so this is my geometry, and then in these two equations we know the structure of the equation, and so we have written, given the source term, and C is 1 by 5 and dA is 0. Similar for the other second equation for variable u2, and if you see again it has the same structure. So both of these are just for the we have just implemented these two equations, like ODE, these two equations, and similarly you need to implement Bratu problem, which is also a 1D ODE problem. Okay, now we need to mash this because we have an interval from 0 to 1, and so this is how the mesh node points look like. You can always change the mesh resolution by selecting the maximum element size. Other option is you can go to predefined settings and select normal or finer or coarser mesh depending upon what you need. But if you go to custom, you can adjust the maximum element size, and if you see in the messages, like it contains, because the element size is 0.05 and we have the total length of this interval 1, roughly 20 elements. It shows 20 elements, and you can change this to make your mesh more coarse or fine. So problem statement, physics declaration in these two nodes, and then mesh declaration here, and then we just need to compute this which we have seen. So it should be pretty similar to what we have seen already in the previous example. So we have seen this implementation of this boundary value problem, and similarly I'll show you this quickly, the initial value problem when you have an ODE and you want to integrate in time. So let me just also show you this example of initial value problem. So again, I have used here the global ODE interface, and the only noticeable change or term is this. See, so now we are also looking at this term, the time derivative term. So the other part is same as how we implemented in the non-linear equation. Now the time dependent term is implemented just by writing t after the state variable. So y1t represents time derivative for state variable y1, y2t represents time derivative for y2, and rest part is similar how we entered in the non-linear case. So this is also very similar, and I hope we have done enough examples using this global ODE interface. Now you should be able to solve boundary value problems, initial value problems, linear, non-linear algebraic equations using this interface. So I'll just gonna close this and go back here. So okay, so we have seen the arc length continuation implementation in COMSOL. So now these are the exercise questions for you. and you're going to work on Bratu problem in COMSOL and also with MATLAB. And I encourage you to try arc-length continuation for Bratu problem in COMSOL. And as I pointed out earlier, there is a difference between COMSOL implementation and MATLAB implementation, which was shown by Dr. Kumar. So I let you figure out the difference. And other thing I want to emphasize is start early on your project work, because it will take some time. So with this I'll end my tutorial on arc length continuation. If you have any questions, just please come back to my office or just write email to me. Okay, thank you, and I hope you learned arc length implementation today. Thanks for your time.